In this video, I want to take a look at type 1 and type 2 errors using the normal distribution. Now, we introduced in the previous video the idea of type 1 and type 2 errors. And what I want to do now is extend this for the normal distribution, which is an example of a continuous distribution. However, there is a slight difference in how we find or calculate the probability of a type 1 error for continuous distributions, such as the normal distribution. So for the normal distribution and other continuous distributions, the probability of a type 1 error is equal to the significance level. Okay, so a nice straightforward concept here. If we had, say, a 5% significance level and we were working with the normal distribution, which is an example of a continuous distribution, then the probability of a type 1 error would be equal to 0.05, right? Because we had a 5% significance level. Now, you might also be wondering about the probability of a type 2 error then for continuous distributions, such as the normal distribution. However, the good news is we find this using the same method as established in the previous video. Okay. Now, before we take a look then at one practice question demonstrating these concepts, let's just quickly discuss the significance then of type 1 and type 2 errors. Now, when we're performing hypothesis tests, what we want to do is keep the probability of type 1 and type 2 errors as low as possible. And this really just comes down to a bit of a balancing act here with the significance level of our test. So for that reason, we'll often just use a significance level of 5%. However, if the results of our test are particularly important, let's say we're looking at the efficacy of a drug or medical screening, then what we will want to do here is choose a smaller significance level, such as 1%. Now, the best way to reduce the probability of type 1 and type 2 errors overall is to increase the overall sample size n. However, this may not always be possible in real life due to either time or cost restrictions. Okay. So, like you can see, and you will often see throughout these types of questions, we will often be using a significance level of 5%. For that reason, that is almost a bit of a balancing act. And 5% just gives us that kind of best middle ground. But be aware that you can use smaller significance levels, such as 1%. So that gives our introduction there to type 1 and type 2 errors for the normal distribution. So what we're going to do now is take a look at one practice question here for type 1 and type 2 errors using the normal distribution. So let's take a look then at this one practice question here for finding type 1 and type 2 errors using the normal distribution. So for this question here, we have the random variable x, which follows a normal distribution with the following parameters. A random sample of 18 observations of our random variable x here is taken. The sample mean x bar is taken to be the test statistic. It's then desired to test mu equals 40, so mu equals 40 here, against mu is not equal to 40, using a 5% level of significance. So for the first part of this question, part A, what we want to do here is find the critical region for this test. So for part A then, we're going to start by finding the critical region. So there is actually a bit of work involved with part A here. And where do we actually begin? Well, what I need to do to begin with here is use the central limit theorem. So we're going to use the central limit theorem. And why is that the case? Well, we have the random variable x, which follows a normal distribution. However, we take a random sample of 18 observations of our random variable x here. Okay. So in that case, we need to use the central limit theorem. And what I'm also going to do here at the same time is assume that h0 is true. Okay. And we assume that h0 is true. Okay. So putting all of this together then, we get that x bar will also follow a normal distribution with the following parameters. So we get 40 here because we assumed h0 is true. So we get 40, and then we get 4 squared divided by the sample size. So 4 squared here divided by my sample size of 18. Like so. Now, what we need to do next is standardize the x bar variable. Okay, so if we do that here, what would we get? Well, I get that z is equal to x bar. We get x bar here minus the mean, which is 40. And this is all over then my standard deviation here. So this is the variance, so I need to take the square root of this, so I get 4. So I get 4 here over the square root of 18. Okay. Now this value here would be equal then, so what I need to do now to get what this is equal to is go to my formula book. We use the significance level here. So this was a 5% level of significance. However, we need to be careful because we have a two-tailed hypothesis test here. Okay. So this is two-tailed. Let's just make a note of that. So in that case, then we need to halve the level of significance here to account for each tail. So in that case, then we are looking at 2.5%. Okay. So go to the standard normal table in your formula book here. Obviously, we use this value of P here, 2.5%. And if you find this correctly, then what you should get here is Z is greater than 1.96. 1.96 there. And Z is strictly less than minus 1.96. Okay. So what I need to do now is set this here equal to plus or minus 1.96. Okay. So in that case then, let me just write this down. In fact, let me just actually simplify this just to make life a little bit easier. This is the same then as taking the numerator and timesing that by root 18. So what I get then is root 18 times x bar minus 40 over 4. Okay, like so. Like we said then, we now set this equal here to plus or minus 1.96. We got root 18. So root 18 times x bar minus 40 all over 4 is equal to plus or minus 1.96. And all we need to do now is solve this here for x bar. And what this leads to then is the critical region for this test. So I'm not going to show the full working here to obtain x bar for both solutions here. What I will do is just give the solutions then. So in that case, what I get here, so when Z is strictly greater than 1.96, so when Z is greater than 1.96 here, what I get is x bar is equal to 41. So I get 41.847, 905, so on and so on. Okay, so that's supposed to be 3 dots there, like so. So this is for Z being strictly greater than 1.96. And then my second solution here for x bar, this is for Z being strictly less than minus 1.96. What I get here then is 38.152094. Okay. Like we said, that is for Z being strictly less than minus 1.96 here. Okay. So now if we give the solution here as the critical region, so therefore the critical region here is, so we get x bar is going to be greater than here 41.847905 because that's for Z being strictly greater than 1.96 here. So 41.847905, and we also have x bar being strictly less than 38.152094. So 38.152094 there. Okay. And there we have it. So that gives the solution to part A. So that's the critical region there, just to get us started. Now for part B, it says state the probability of a type 1 error for this test. Now, don't forget, for a normal distribution, which is a continuous distribution, the probability of a type 1 error is simply equal to the level of significance. In this case, 5%. Okay, so the probability then of a type 1 error is simply equal to the significance level, which in this case is 5%. That would be 0.05 there. Okay, nice and easy there for part B. And then finally for part C here, it says, given that the true value of mu was later found to be 43, find the probability of a type 2 error. Right, so for the probability of a type 2 error, let's just write this down then. Type 2 error. What do we require here then? Well, I require now the probability that our x bar variable here is between these two values. Okay, so in other words, we're not within the critical region. Okay, I've got 38.152094, and then we have the upper bound here of 41.847905. 847,905. Okay, and this is conditioned on the fact then that mu is later found to be 43. Okay, so given that mu is equal to 43, like so. So all I need to do now is use my calculator here to find this probability. So we're going to stats mode. So stats mode, distribution normal. So in this case, clearly this is a cumulative probability. We don't use NPD anyway for the normal distribution. So NCD. So the data here is a variable. So my lower value is this value here, 38.152094. My upper value then is this value here, 41.847905. Mu and sigma then, well, they come from this here. Okay, so let me just change those. So mu is 40, and then for the standard deviation, like we said, that would be 4 over the square root of 18. Okay, all we need to do then is press enter here. I'm sorry, mu would not be 40, mu would be 43. Don't forget, we've conditioned on this fact, so don't make that mistake like I nearly did. So mu is 43, there we go. And then if I give my answer to a sensible degree of accuracy, let's say 3 significant figures here. So let me just write down everything here. So lower is this value, upper is this value. Standard deviation then, sigma, that's this here, but the square root of that obviously, so 4 over the square root of 18. And then for mu, because we've conditioned on the fact that mu is later found to be 43, mu equals 43. Okay, lower is this value. So I'll write that underneath, lower. And this here is the upper value. Okay, input those values and then press enter. And what you should get then, like I said, if you give this to a sensible degree of accuracy, let's call that 3 significant figures, we get 0.111. Okay, and there we have it. So that is the probability there of a type 2 error using the normal distribution. And there we have it. So that gives the solution to just the one example here in this video. So question 1, and that actually brings us to the end of this video on finding type 1 and type 2 errors using the normal distribution.